Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of CUDA Crash Course, we're going to be going over how we should be thinking about programming GPUs with this idea of thinking spatially. So starting out, we've got to go over, what's kind of key idea behind this, and that really stems from what's the difference between a CPU and a GPU. So a lot of us are familiar with CPU programming, but not so much with GPU programming. Now, CPUs are optimized for latency, and they support very complex control flow. So we can have very complex applications like some, multi-million line of code database piece of software. But GPUs are optimized for throughput, and this has a number of implications. So we don't have things like branch predictors or out-of-order execution, and the kind of control flow that we want inside of our programs, we want it to be very simple, and it's because a lot of times because of the SIMT architecture. Now this really just means that we have a single instruction for multiple threads, meaning that if we want different threads that are grouped together to do different instructions, this ends up being serialized execution. And we call this warp divergence, and we don't want that. So we want to simplify our control flow so that all the threads are kind of doing the same thing. And we want different parts of our execution to be mapped to different places. So that really leads into this idea of temporal programming on CPUs versus spatial programming on GPUs. So what does spatial mean? So we first have to say, what does temporal mean? So when I say temporal, what I'm referring to is the idea that what basic blocks we're executing really depends on when we are in execution. So a number of pieces of research have looked at this, and they found that temporally you can find patterns in execution and benchmarks and in real world applications, but these things happen over time. And so an example of this would be maybe in some piece of software, we collect some data for some period of time, then we process that data, and then sometime later we go back to collecting that data. But this is something that's laid out temporally, or it's temporal in nature, right? So it happens over a span of time, and during that time you'll be doing different things. So if you think about single-threaded code, this will look like an instruction manual. So you go down and you'll do instructions, and maybe an instruction tells you to go backwards, but at the end of the day, you're just following down a list of things to do in order. Now, when we're talking about spatial programming, which is what I'm going to refer to when we're talking about programming for GPUs, which basic blocks are entered and executed, a lot of times this depends on where a thread is mapped. And so when I say mapped, let's just kind of define what that means. So when we're programming, say in CUDA, we define a grid of threads that we basically overlay onto our problem. And so this is an example of it over to the right here. So, we've got different levels that we can make something multidimensional. So we can have all of our threads here. We can have a three-dimensional grid of threads. And then those get packed into cooperative thread arrays, also known as thread blocks. And then over here, right, this green, this represents our grid. So we can have a multidimensional grid as well. So we can have these CTAs or thread blocks stacked in, X, Y, and Z coordinates. And so basically we can have, 1D, 2D, or 3D arrangements of threads that we can use to map to our problems. Now, why this is important is the fact of this second picture I have down here, which actually comes from my own research. So this is a comparison of different warps. Now a warp is just going to be a group of, in this case, 32 threads, right? And what I'm doing is I'm comparing the basic blocks executed by each of these groups of 32 threads. So this comes from a benchmark, from the Rodinia benchmark suite. And so for this kernel that launches 4,000 warps, we compare, warp 0 against warp 0, warp 0 against warp 1. We're comparing the number of basic blocks executed, or rather, all the basic blocks executed by a single warp, we're comparing it to all the basic blocks executed by another warp, and we're finding the distance, in this case the Manhattan distance between those two vectors of basic blocks. And what we see are these interesting patterns. And so what it turns out that spatially, when we compare different thread locations, right, so different warps, what we see is we get some very neat, interesting repeated patterns. But these repeated patterns don't exist like they would in a CPU program, over time. They exist spatially, right? So it exists spatially within this grid of threads that we've defined for our problem up here. So that's really the difference that I'm trying to say between temporal programming and spatial programming. So let's go through a couple examples of how we can think spatially about GPU problems. And we'll start with the hello world of GPU programming, which is vector addition. Now with vector addition, it's a very simple problem that's embarrassingly parallel, which basically just means that all of these operations that we're doing, adding two vectors together and all the elements of two vectors together, they're all independent of each other, right? So to calculate 2 as 1 plus 1, that's completely independent of calculating 4. So if we're thinking about this in terms of a CPU program, what we do is we think, okay, well, temporally I have to think about this in terms of a loop. So on the first iteration of the loop, I'll add the first elements together. The second iteration, I'll add the second elements together. But when we're doing something like GPU programming, right, I can flatten this out and basically spread it spatially across a grid of threads. Now our grid in this case ends up just being one-dimensional. It ends up just being a big long line of threads. And what I can say is that, okay, well, what happens if I just map each of the final elements to an individual thread, and then each of these individual threads will do this 1 plus 1 or 2 plus 2. So then I don't have a for loop anymore. What I'm calculating is based upon my position in this big long line of threads. And there's cases which happens quite frequently where we have an element that shouldn't actually do anything, that we just end up having to pad. So we have to take care of that in our code itself, right? But this is just a function of the fact that instead of having something that's being done in a loop, we have to map some grid onto our problem, right? And oftentimes we don't get a perfect fit. Now we can continue on and talk about this in terms of how do we figure out where we are spatially. So it's important that we understand what we have available to us. So the first thing is we have this variable called grid dim, which stands for the grid dimension. Now, like I said earlier, our dimension can be, or our grid can be three-dimensional. So this .x could be .y or .z, and this just says how many thread blocks or CTAs do I have in a particular dimension. So in this case, I'd have 4, right? So this would be 1, 2, 3, 4 different CTAs or thread blocks. Now, how we figure out where exactly we are is basically a function of our block ID, our block dim, and our thread ID. Now, our block ID just says which block am I within a particular dimension. So in this case, the x dimension. So this one will be 0, this will be 1, this will be 2, this will be 3, if I consider this the x direction. Now, likewise, just like there's a grid dim, which says how many blocks there are in a particular dimension, there's also block dim, which says how many threads there are in a particular dimension. So like I said, we can define these grids that have multiple three-dimensional components. So we can have three-dimensional arrangements of threads and three-dimensional arrangements of CTAs or thread blocks. So here when we're saying block dim, we're saying how many threads are in a particular direction. So here we're saying how many threads are in the x direction. We have 2 threads, right? 1, 2. Now to get these individual threads, just like we have a block ID, there's a thread ID, right? So this will end up being thread 0 and then thread 1, right? So these are just 0 indexed. So it turns out to find our position in this big long line of threads, it just turns into a base and offset calculation. So if I go ahead and just annotate here, this is thread 0, 1, 2, 3, 4, 5, 6, and 7, right? So this is where I want to figure out. So my own understanding, not thinking about a computer, but just my own kind of high-level understanding of this is that I'm launching 8 threads on the GPU. And to figure out where I am, I first need to figure out which block I'm in, and then I need to figure out my offset within that block. And that's a simple base offset calculation where we do block ID x.x times block dim.x plus thread ID x.x. And so if we do that for, say, this thread right here, what we end up getting is our block ID is 3, our block dim is 2, so this just says how many blocks do I have to skip. In this case, I need to skip 3 blocks, which is the equivalent of skipping 6 threads, so 3 times 2, and then I just need to figure out my offset within the block that I'm at. So in this case, my offset here would be 0, my offset here would be 1, so I'll do plus 0. Right, and these are all filled ahead of time. You don't need to worry about, oh, do I need to set these special registers? No, these are just available for you. You just need to access them through these variables like block ID x.x, thread ID x.x, etc. And this is also how we mask off certain elements, right? So if we don't want to have a certain thread continuing on with execution, because just like we saw here, some threads we might have to pad our grid with some threads just because of the fact that we have to launch equally sized thread blocks. We'll just have like a simple if statement at the very beginning of our code that says, if this exceeds some bound, you don't do anything, and it will just be masked off for us. So that's a simple 1D example, but a lot of times our problems aren't one-dimensional. A lot of times we're doing things like matrix multiplication on GPUs. So let's talk about that. So here, a matrix like this is 2-dimensional, right? So it has a row and a column. And so we'll generally represent this using a 2D grid of threads, right? So in this case, instead of having a big long line of threads, where each thread will calculate one element in that 1D vector, now each of our threads in this 2D matrix of threads, or this 2D grid of threads, will calculate one index in the matrix that's a row column, right? So we'll say that this thread right here will calculate C00, this thread down here will calculate C11, etc. And the basic operation we're doing, if you're unfamiliar with matrix multiplication, is that to calculate C00 in this case, in order to calculate this, this thread right here will have to do A00 times B00 plus A01 times B10, right? So we're going over the rows of one matrix and down the column of another matrix. So, but we need to think about this spatially because we're mapping this 2D grid of threads onto a 2D matrix. So like we just did with the 1D example, right? So instead of doing this, this base offset calculation, what we actually want to do now is a row column calculation. So instead of just finding where we are in this big long line of threads, we want to find a row column pair that represents a unique thread. So in this case, we use the same variables, but what will change will be at the very end, you'll see a .x or a .y, right? So here, this grid dim.x says how many blocks are there in the x direction? Well, there's 2. And over here, this .y says how many blocks there are in the y dimension, and there's 2, right? So 1 block, 2 block, and then x direction, 1 block, 2 block. Now, if we take this block in particular, right, it will have its own unique block ID x.x and block ID y.y. So here, the block ID x.x, right, so these things are 0 indexed, so it's in 0, right? It's in the 0th column, right? So this is column 0, this is column 1, this is row 0, this is row 1. So if we want to find the index of this block, it'll be 0, 1, right? So the 0th column, and then it'll be the first row. Now, this extends down to within a block itself. So when we're talking about the thread ID x.x, we're talking about within a block. So if I want to figure out who I am locally within a thread block, I'll do, say for this thread ID x.x will be 1, right? So thread, this will be 0, this will be 1 in the x direction, and then the y direction, again, 0 and 1. So if I want this thread's coordinates locally within a thread block, it will be 1, 1, right? But what I really care about is globally, right? So I'm putting my grid over some giant global matrix. I don't always care about, or what I really care about is sometimes, and usually when we're talking about accessing a big, large structure in global memory, I care about finding where I am mapped onto some giant matrix. So in this case, I need a combination of block dim, which just like grid dim says how many threads there are in a particular dimension, just like grid dim says how many blocks there are in a particular dimension. So to figure out who I am globally, it's the same kind of base offset calculation, but instead of just giving us our exact position, it'll give us one element of it, which in this case will be the row and the column. So to get the row, it'll be the same calculation for base offset, but it'll be in the y direction. And the column will be the same calculation, but in the x direction. So in this case, it'll be block ID x.y times block dim.y plus thread ID x.y. And likewise, it'll be the same calculation, but with x for the column. And so how we can visualize this is, let's take, this thread in particular. So let's delete, let's get rid of some of this drawing. Right, so we're really concerned about, this thread globally. So if we look at the row, right? So for the row, let's get rid of some of this highlighting as well. So right here, it says, okay, what's my block ID X, right? So as we know, in the Y direction, this will be block 0, this will be block 1. So that's the block ID that I am. Now I care about how many threads there are per block, because that's how many threads I have to skip. So that's going to be block dim.y, right? And so in this case, there's 2 threads per block, as we saw here. So I need to skip 2 threads in the Y direction to get to the beginning of this block right here. Then I need to figure out my offset in the Y direction in order to get this thread, which is going to be 1, because this is thread 0, this is thread 1. So I end up with the calculation of 1 for the block ID times 2, the block dim, that gets me down to this block. And then I need to get the offset in the Y direction for which thread I want, which is 3, right? And so this is just telling me you're in row 3, right? And if we go ahead and list these out, it'll be rows 0, 1, 2, 3. So if we do the same thing for the column, it's the exact same calculation, just in the X direction. So we have column 0, column 1, column 2, column 3. So then we find the block ID x.x, right? And so we're in this first column, so it'll be 0. Then we need to get the dimension of how many threads we need to skip over in that direction, which will be 2, but this is just 2 times 0, so we stay in the same spot. And then the offset in the thread ID x.x direction, right? So the offset in the x direction. So am I in this column or am I in this column? And because we're talking about this thread right here, we're in the 0th column, so it will add 0. And what we end up getting is this pair of xy coordinates of 0, 3, right? And so this just says you're in the, right, or we can do it, so this just says I'm going to be in the 0th column of the 3rd row, right? So we're going to be right here. And so probably it'd be better to write this as 3, 0, right? If we're doing row column, right? So this is the thread that we just found, and it's just through 2 calculations, one for the row, one for the column. So moving on to this of why this idea of thinking about things spatially matters is because when we're doing optimizations like cache tiling, we need to think about problems spatially. So again, this is matrix multiplication, but we want to start doing optimizations like how can I, increase the locality that I have. So I know with this big matrix, I know that these 2 threads right here, so let's just highlight these 2 threads right here will both go over every single element in this row because they'll calculate these elements inside of C. And so the only thing that's different between these 2 rows and what they calculate will be the first one will go down this column, the second one will go down this column. But they share a lot of locality in the in this row because they'll all access the exact same elements. And likewise, when we're talking about the columns, right? So these this column right here, right? So these 2 elements inside of this big matrix, they'll access different rows in the A matrix, but they'll both access the same column in the B matrix. So I'd like to load these a bit early. So it's basically the idea of prefetching. So we're prefetching values into what's known as shared memory, which is very fast memory, but I need to be able to think about this problem spatially, right? And so a lot of times when I'm thinking about these problems, I go, what is a single thread going to do, right? And then I can just scale that up and go, okay, well, what is a small group of threads going to do? What is a thread block going to do? And then after I figure out what a thread block is going to do, that's basically the problem, right? So if I figure out what one thread block is going to do, that's pretty easy to scale up to. Okay, well, every thread block will be doing that same operation, so I just launch more of them. So, but in this case, what we're doing is we'll have to load this small subset of matrix A and small subset of matrix B into what's known as shared memory, which will be smaller structures that are much faster and inside the core itself. Right, and then locally we'll just do some local, we'll compute locally for these small submatrices before we finally get our result. And what will happen is every iteration of the loop will just move this tile over. So in the first iteration of some big outer loop where we're doing this, what we'll do is all these 4 threads will load these 4 values into this submatrix right here. And then in the next iteration of the loop, this tile will move over like we've shown here, and it will load in the next 4 values, right? But I need to be able to think about this spatially, because I need to think, okay, well, I've got a tile sweeping over a matrix, which means I've got these 4 threads in this case sweeping over a matrix. And likewise, in the case of B right here, I have these 4 threads going over this first tile right here, but then in the next iteration, I want them to load these 4 elements into this matrix right here, this submatrix rather, right? And C is just going to stay the same because C is just being used to accumulate all these partial results. And then at the very end, after we've swept these threads over the entire row and entire columns of these larger matrices, C will automatically have its solution, right? And so this is just another way that we have to think spatially about our programs. Right, so another reason why we have to think spatially is for something that's very architecture dependent, which is the idea of coalesced accesses. Right, so going back to our matrix multiplication example, you know, all of our threads right here, let's go back one. So our threads are going to be accessing data inside of the B matrix. They're going to be accessing all down the columns. So these 4 threads will all be going down these 2 columns, right? So if we look at that in terms of just the accesses to the B matrix, and say if we had, you know, in threads going out to the side, you know, memory's laid out, in this case, in row major order, so which means that a 2D structure like this is going to be flattened into a 1D big long line. So when we're thinking about this, we have to think about, are we accessing contiguous pieces of memory or non-contiguous pieces of memory? Now, in this case of the B matrix, all of your threads are accessing independent columns, but independent columns will all be mapped to a contiguous region of memory. So in this case, we can have what's known as a coalesced access in a GPU. So all of this access to this big, you know, piece of data will all be merged down to a single wide access. Now, let's go back for just a second and look at, you know, for the rows. So now these 4 threads will all be accessing different rows. So how is this going to differ in terms of the memory system? So in the memory system itself, you know, accessing these independent rows, so, you know, every single cycle we're going, or rather every single step of matrix multiplication will access, you know, everything from all the rows and then everything from all the columns, right? And then we'll do multiplication, and then we'll add that to a partial result, and then we'll move over, you know, we'll move over next to the next column, and we'll get everything from those rows. And likewise, when it comes to the columns, we'll move down by 1. So what happens here is that, you know, this will end up getting mapped once we linearize it into the way memory actually looks. All of these accesses will actually be spread pretty far apart. Now, in this case, with a simple 4x4 matrix, you know, you could get all of these in a single access, but you have to keep in mind, think about how big a matrix typically is that we're working on a GPU. So this is probably not going to be a 4x4 matrix. What this is going to be, you know, this could be 1,000, you know, or 1024 elements inside of a row. So this gap right here is actually going to be 1024 elements. And because of that, you're going to basically have a bunch of individual accesses, you know, to get each of these elements. Now, there's a number of things we could do in order to fix this or to improve this, and one of which is, you know, doing this idea of pre-processing. So instead of having a bunch of these individual, or instead of having to do everything on the GPU and just suffer with bad non-coalesced accesses like this, what we can do is we can take this matrix, we can transpose it ahead of time. So just like with the columns, we have the exact same layout for our rows now, and then we just need to change our the way that we iterate, or the way that we index into that A matrix now, so that we're accessing it in the same way as the B matrix, so that everything's going to be coalesced, right? So this really only comes though from an idea of thinking spatially about our problem, right? So thinking about a single thread isn't going to help you solve this problem, right? Because a single thread is just accessing a single element at a time. So you have to think about this in terms of, you know, spatially, what are all of these threads accessing from a particular matrix, right, or a particular data structure. So what can we conclude from this? So programming GPUs it has unique requirements, right? So it requires a fair amount of spatial reasoning. We have to think about how our threads are mapped to our data, and what that in turn means for, what will be executed, if executed at all. So are we in a part of our grid that's, past the edge of, say, an image that we're processing? In that case, we shouldn't execute anything, right? Because we're accessing, no data. We also have to think about the underlying architecture, right? So, when we're accessing data in a spatial manner, right? So if we're accessing data in terms of, all these threads are accessing, all the columns of a particular matrix or all the rows of a particular matrix, we have to think about what does this mean in terms of coalescing. That's really the big issue there. But, another key takeaway is that GPU programming is not impossible, right? So a lot of people, there's a big learning curve to get into GPU programming, but what we have to think about is this idea that, normally in CPU programming we have, loops, and this isn't to say that we don't have loops in GPU programming, but loops in GPU programming end up turning into index calculations, right? So inside of vector addition, for example, we'll have a single for loop in a CPU version that does, for I in range of the length of a vector, right? And then you'll just iterate over every single element. Now, this gets turned into just your global grid thread calculation inside of a GPU. So a loop basically just gets spread out and flattened into a grid of threads. And so we have to think about programming in terms of, the spatial nature, not a temporal nature like we would a loop. So, and then the other thing is that understanding this conversion, at least for me, it requires practice, right? So I didn't understand exactly how the cache-tiled matrix multiplication worked until I actually coded up myself and practiced with it. And a lot of times it's really useful to just use some scratch paper, right? So if you draw out a simple example, a 4x4 matrix, please don't do a 1024 by 1024 matrix by hand. It's not going to help you at all. But sometimes, visualizing things in terms of, doing a small diagram like this and to try to understand, spatially what are your axis patterns going to look like, that can help you a lot as well. And, this is really one of the big things that'll help you understand how, your GPU programs will actually run and how you can even map, your particular application that isn't vector addition. It's not matrix multiplication, but it'll help you map arbitrary applications that may have a ton of parallelism onto a GPU. But that's going to do it for this episode of CUDA Crash Course. As always, all the code for all of my series is available on GitHub at github.com/coffeebeforearch. So for the CUDA programming series, we can go to CUDA programming, right? We have sections on, environment setup in Linux and Visual Studio, stuff like vector addition, matrix multiplication, some reduction and convolution, including optimizations for all of these. So feel free to check any of these out. The code is posted for each of these, as well as links to the YouTube videos. But that's going to do it for today. I'm Nick from Coffee Before Arch, and I hope you have a nice day.